Hi, and welcome to this part 2 of the metrology course video. If we recall, in our part 1 of the metrology video, well, we looked at definitions. We also looked at how averaging can help with the precision of the measurements that we make. And we also looked at 2 ways to perform measurements: direct measurements and comparative measurements. Today we're going to start out by looking at 2 types of measurements, which are really the 2 types that exist of measurements for our geometric measurements. That is, we're not here to talk about measuring heat or speed. We're here to talk about measuring surfaces. And for that, we're talking geometry. And for measuring geometry, we really have 2 types of measurements: linear measurements and angular measurements. And you're going to say, well, what about curves? Curves are linear measurements because a curve is always broken down into its x and y coordinates. Okay, well, what about our 3-dimensional curves? Well, it's the same thing. It's just x, y, and z coordinates. Now, it's important to remember that we saw in our first video that there were direct and comparative measurements. And now I'm talking about linear and angular measurements. Well, it's important to say that in linear measurements, we can use direct measuring tools and comparative measuring tools. And that in our angular measurements, we can also use direct measuring tools and comparative measuring tools. So the direct and comparative measuring tool theories work in both linear and angular measurements. Now, let's look more specifically at our linear measurements. Now, a linear measurement is, as the word says, a measurement that is in a straight line, linear. And for that example, well, we could use this 1, 2, 3 block. If I measure from one place on one surface to the same spot on the other surface, in other words, perpendicular to the surfaces that I'm measuring, well, I'll be performing a linear measurement. And we can perform those measurements with rulers, with calipers, with micrometers, with height gauges, with all kinds of instruments. And we're used to that type of measuring. But what about curved surfaces? Well, if I look at a regular curve, let's say a cylinder. Here's a brass cylinder. It's actually a brass punch that it's just nicely turned because I just cleaned it up. So here's a nice brass punch and it's a cylinder. Well, how do I measure this cylinder? Well, I measure it linearly from one end to the other of the circle. So from one point to the other, perpendicular to the axis of the cylinder, and a measurement that goes through its center axis. If I do that, I'm measuring linearly, but I'm determining the diameter. Now, how can I make sure that it's round? Well, I do the same measurement on several different spots around the part. And if I get a constant reading, well, my part is cylindrical. If I don't get a constant reading, well, there's some oval problem with my part. How about parallelism? Ooh, how about parallelism? Ooh, that's a difficult one. Well, if I measure at several spots along the length of the part, even though this is a curved, round part, well, I can determine its parallelism. Oh, I'm having a hard time with that. Parallelism. Okay, and it's still linear measurements. Okay, well, let's see, we push it one step further. Now let's take a look at a 3-dimensional curve. And here we have a test run of an NC profile program that I performed many years ago. I was just a young man. And it's the underneath of an air intake for a CF-18 or an F-18 fighter, a 6% model. And I have a roughing pass and a finishing pass. This is a good example of a three-dimensional curved surface. But if we look at it closely, we can see that we have lines in all directions because it's just a series of points. The ball noise end mill that cut this surface moves from one point to another, and in each move, well, it's going to move in X, Y, and Z for each spot it's aiming for, the next one coming up, and eventually adding all those spots up together and the movements between them, well, we end up with this lovely three-dimensional curved surface. Very complex surface. Knowing that there's several types of measuring instruments out there that can perform linear measurements, remember both direct and comparative, well, the question can be asked, how do I choose the proper measuring tool? Well, obviously there's a myriad of tools, each one specifically made for one or several types of measurements, or situations of measurements, I should say. Well, fine and dandy. But if we want to not go through the long list, which isn't something that I feel like doing, well, we can do it a little more philosophically and say that very accurate tools should be used on very accurate parts. Rough parts should be measured with inaccurate and rough tools. You would never use a micrometer to measure a rough casting. No, you'd use a steel ruler to measure a rough casting. If you did use a micrometer, well, you wouldn't just be wasting your time. You'd be probably damaging a very expensive tool. And the end result, because the part isn't accurate, wouldn't be one iota better than if you used a steel rule. So that is the golden rule. Choose an instrument that will give you a proper result as far as the quality of surface finish and precision of the part that you're measuring goes. Rough parts, inaccurate measuring tools. Highly finished and accurate parts, accurate measuring tools. It's basic and quite simple, but a lot of people don't follow that rule. Another thing that's important to remember when selecting measuring tools is that the measuring tool that you select should be a lot more accurate than the part that you're trying to measure. So that would mean that if you wish to measure a part that has a 1/1000th of an inch tolerance, well, you're going to want to use an instrument that has its tolerance around the 1/10,000th of an inch range. Or if you prefer, 10 times more accurate than what you're trying to measure. Now, you must never confuse how accurate a tool is with how accurately you can read it. A vernier micrometer. Let's say we get a Starrett vernier micrometer and a Starrett standard micrometer, both 1 inch. Well, one can be read to 1/1000th and one can be read to 1/10,000th. They're both as accurate, but one can be read more accurately than the other. They don't produce the inch standard micrometers sloppier than their 10,000ths of an inch micrometers. And they're produced in the same fashion. So they are very accurate tools, and they're accurate in their fabrication to a very high degree, okay, even if the scale isn't that accurate. Another example is a good steel rule. Well, a good steel rule can be read to a 64th of an inch without any hesitation or problem. Does that mean that it's made to a 64th of an inch tolerance? No. A good steel rule is very accurate. The lines are well within a couple of thousandths or even within 1/1000th of an inch as far as their positioning goes, even though we can only read it to a 1/64th. So you need accurate tools to measure accurate parts. And finally, if we're talking about tool selection, we can't ignore availability. Now, there is a myriad of tools out there, I've already said that, and you could go bankrupt trying to buy all the specific tools out there that'll make your life a little easier. And it's fun to have these tools, they're great time savers, but for the home shop aficionado, remember, speed isn't your forte. You're going to have to take time to think about what you're doing, and you don't want to go bankrupt having fun with your hobby. So what do? You buy basic tools and you learn to work around the problems, okay? You can do most measurements that require precision in the shop with some very basic measuring tools. So let's take a look at those basic linear measuring tools in the shop. My basic linear measurement tools in the machine shop are, and they're out here with me now. Well, the first one to consider, and it's really important, is the surface plate. We don't tend to think of it as a measuring instrument, but it is an integral part of linear measurement, because most of my comparative measurements will have as a unified starting point that surface plate. And I have two here. I have a black granite surface plate, a small one right here, and I have this larger old gear that I've turned into a cast iron surface plate, and it's quite flat and quite stable. It's something I made for myself some 35 years ago, and cast iron is quite stable as long as it's been weathered and it has some age. It has to sort of relax over time. Now be careful at the front here. I've put another thing that looks like a surface plate, and it has these grooves, these angular V grooves cut into it, and it is quite flat, a bit like a surface plate, but it's actually a lapping plate, and that's for lapping, in this case, small parts, because it's a small lapping plate to be used with abrasives in paste form. So be careful not to confuse a lapping plate with a surface plate. After that, we have, in an increasing order of precision, well, our steel rulers. Now these are accurate steel rulers for machine shop measurement, not for drafting. We'll talk about that in a few minutes. And then we have our calipers, vernier calipers, or dial calipers, or electronic scale calipers. Our calipers, then we have our micrometers, and then we have our dial indicators, and finally, in our basic shop tools, we have a small set, doesn't have to be a complete set, but a small set of gauge blocks. So let's take a look at these one by one. So if we look a little closer, we can see our black granite surface plate, very small, quite attractive, very precious little surface plate. And we have my big ugly old gear of a cast iron surface plate. Advantage, disadvantage? Well, advantage, definitely a lot more stable. This granite is hardly affected by temperature and will not warp. It's quite stable, which isn't really the case for this cast iron one, even if it's weathered and has been stabilized by the years. Also, if I should happen to nick or pit this granite surface plate, well, it will pit, but it will not mushroom, so I don't get a bump on it. So even if there's marks and imperfections, I stay flat, which really isn't the case for this cast iron one. Now, on the downside, this granite surface plate is going to be a lot more expensive than an old gear that I've machined flat and made into a surface plate. But it's a lot more reliable also. So depending on how accurate you have to be, a granite is probably the best way to go. But be careful, they are quite delicate. Even if they look massive and they're quite hard, if hit the proper way, they will shatter into several pieces. so you have to treat them delicately. And even though they're quite large, remember, they are a precision measuring tool. So do treat them very delicately and with a lot of respect. And as I've mentioned before, this front plate here, which is quite flat, I mean this is almost or pretty well as flat as this granite surface plate, well, it's not a surface plate at all. It's a lapping plate, and you can tell by these V-grooves in the surface that are there to accumulate small amounts of abrasive paste. And this obviously is used to lap small parts, to lap a surface very flat. And you can see a lapping plate, although it's a finishing lapping plate that doesn't have, or no, it's a roughing lapping plate that has the grooves. In the video, I think it's part 3 of the 1, 2, 3 block video. Anyways, I'll put a link down here to see that one. And now don't confuse these with surface plates. Lapping plates aren't surface plates. If we take a closer look now at our steel rulers, we can see that we have all types. We have short and flexible, a little more rigid but still short, and imperial, metric, a little longer, quite long rigid. Here we have a foot long rigid, which is my wife's favorite tool, and a multi-scaled ruler here that goes from 64ths of an inch to 1/8 of an inch, all in one scale. So these are our basic rules, and we have all kinds. But what's important about these machine shop steel rules is they aren't just scales. Now when we have drafting rulers, we're looking at the scale and the straightness of the edge that's quite often beveled for drafting. In this case, our edge is flat, and that is important because this isn't just a direct measuring tool, it's a comparative measuring tool, and that side edge is a straight edge that can be used for comparative measurement. In this case, as example, to measure flatness, okay, using some shim stock as an example. Now, that's the edge of the tool, but the end is quite important also. And this end of tool is the reference surface for the scales. On a machine shop ruler, the scale starts at the very end of the ruler, which isn't the case for a drafting ruler. Now, if I damage this end in any way, this ruler is no good. So it's really a precision tool that we have to take quite care in handling because we want to maintain its geometric integrity. It's very important. If we look at the lines on the scale of a machinist ruler, the first thing we notice is that they aren't painted on, although they can have some dye in the bottom to make them pop a little bit, but they're actually grooves. They're not protruding from the surface, they really go in. And that's important because that permits us to insert a tip into one and know that we're stable and exactly on that division. And in that way we can set, example, a set of dividers to a specific width. Now, it's also important to know that on these scales, the lines have a certain width, and it's normal, they're grooves. It is the center of the lines that represent the proper dimension, so that's important to remember. Well, you think that'd be enough. But no, machinist rulers come with a lot of accessories, and accessories make them a little more versatile. So let's take a look at some of those accessories. The most common accessories for a steel rule in a machine shop, well, is the accessories that come with a combination set. And that is a 4590 square that incorporates a bubble level and a scriber, as well as a protractor, also incorporating a bubble level and rotation at 360 degrees in degree divisions, very important, as well as a center head. Now this one baffles a lot of people, but it's so simple it's not even funny. It's just that we're not used to using it, but it's really just used to center parts In other words, to find a part's center. So if we take our center head and we install our rule on it, we can see that the edge, the straight edge of this accurate tool comes right through the center of this 90 degrees. And obviously, and here I'm going to use the scriber from the 4590 square, and obviously if I scribe two lines here spaced out by somewhere around 90 degrees, well, their intersection is going to be on the center of the part, thus the name center head. Now, the protractor I don't think we need to explain very much about. It's for angular measurements, and we're going to be looking at angular measurements in the part 3 of this series on metrology. And the 4590 square, well, that also doesn't need much explanation, but I'm still going to install this so that I can show you that if put flush, this is not only a reasonably accurate square, but it can also be used as a kind of height measurement tool, since the end of the scale is the zero or starting point for this measurement scale, and that it's even with my surface plate. Well, it becomes an interesting height measuring tool, and we can see this being used in our little quickie video about doing the scale on the drill point gauge, or how to make the scale on the drill point gauge. There's a link for that here also. So, interesting set of accessories for a steel ruler. Now, that's not all the accessories, but this combination set really should be in every beginner machinist toolbox. Now, another interesting set of accessories are these. Now, if I use just one, I create what is basically a hook rule that I can use to hook onto a part to stabilize my measurement and to be able to measure in a repetition type way several parts, all from the same datum or reference surface. But if I use a couple of these on my ruler, well, I produce a stand that stabilizes the ruler and that can be placed on the surface plate so that I can bring parts up to it and measure almost in a reverse way. But that's not really the use of these. They're mostly used for putting a ruler onto a cylindrical part, and that is really nice to be able to scribe lines lengthwise on a cylindrical part, and even to stabilize this for measurements because it frees up both my hands and permits me to work a little more precisely. So, another accessory that can be interesting. And finally, for today, I'm going to be looking at this little accessory here, which basically turns your rule into a square, but we already have this for that, so that's not really necessary. But take a look at this. So let's say we do that, and we do this. Okay, and then we're going to add to this my vernier caliper. Okay, so I've created a tool that will permit me to measure groove depth on a surface that's perpendicular to my reference surface. It's not something that we'd use very often, but it's an example of what you can do with rulers to make them more versatile. One of the purposes of these videos is to tie all my videos together, these theoretical videos or theory class videos. And that's going to work because, as you can see, we still have a few tools to look at. Our gauge or Joe blocks, our micrometers, and our vernier calipers, as well as our dial indicators. And those tools have been covered fairly well already in other videos that I've produced. So I'm just going to be putting links, and here's a link to the micrometers. It's a little quickie. Here's a link to the vernier caliper. Here's a link to Joe blocks or gauge blocks. Now, obviously the dial indicator isn't a specific subject, but it has appeared in many of my videos, so we'll have to jump around a bit, but we can get a good idea of our dial indicator through the other videos. Now, the only thing that I'll mention that I don't think I've mentioned in other videos about the dial indicator is that it's mostly a comparative measuring tool, but can also be a linear measuring tool or a direct measuring tool if I read the scale. But if I do use it as a direct measuring tool, I have to assure myself that my movement is perpendicular to the surface that I want to measure. If I'm measuring vertically, well, it has to be positioned very perfectly vertically. If it's at an angle, I'm actually going to be measuring the hypotenuse of a triangle, which isn't at all the result that I'm looking for. So just make sure that you're properly aligned if you use the dial as a direct measuring tool, a linear measuring tool. So if you don't like clicking on links, and I can well understand that, well, let it be known that all my videos are available on my website, THATLAZYMACHINIST.com. You don't have to sign up, you don't have to be a member. You just go to THATLAZYMACHINIST.com and look through the website to find the videos you want to watch. It is a self-made website, and it has to be probably the ugliest website I've ever seen. But it is what it is, and thanks to the good people at GoDaddy who helped me quite a bit, I managed to get that together. But it seems to work, so if you want, you can go there and look at my videos, and you don't have to click on the links. Next time we'll be moving on to our part 3 metrology video that's going to be all about angular measurements and gauging. So that'll be fun to look at. And after that, well, we'll be moving on to a couple of videos about blueprint reading. Now, there's a subject that'll keep you on the edge of your seat, but it's really important stuff to know. It's not a full-blown course, but we're going to be hitting the most important things and the things that are most often not well understood in blueprint reading. So, until then, happy machining.
There you go.